2005 A-Level Combined Mathematics Paper 2, question number 1. This video is being done outside of my normal schedule due to the special request of @user-wm8iz6hy3f. If you yourself have such special requests for videos of either lessons or videos of past paper questions such as this one, then post them in the comments down below or in the comments of my other videos, and I will most likely make similar videos on those topics. Now moving on to the question, the first part of the question, part A, says a particle A is dropped from rest at height h above the ground at time t equals 0 and falls vertically under gravity. So it's basically dropped at 0 velocity and it falls down under gravitational acceleration of g. At the same instant, another particle B is projected vertically upwards from a point on the ground with velocity u. Now given this setup, we are asked to draw the velocity time graph for the motion of each particle on the same diagram, and then using the velocity time graphs we are asked to show that the two particles are at the same height from the ground at time h over u. Now after that, the second part of the question says a ship sails with uniform velocity having components of u and v eastward and northward respectively relative to the water. So basically the ship is moving east and north, and the eastward direction velocity is u like this, and the northward vertical velocity, which is perpendicular to that, is v like this, and the resultant of these two is a velocity in the northeast direction like this. So given this, it says when the ship is at a distance d north from a submarine, a torpedo is fired from the submarine with the intention of destroying the ship. Assuming that the torpedo moves uniformly with velocity of w relative to the water, we are asked to show that if the torpedo strikes the ship, then w must be greater than u, and given that we are asked to find the time taken by the torpedo to move from the submarine to the ship. So basically there's a setup where we have a submarine and a ship, and the submarine launches a torpedo towards the ship such that it hits the ship, and we are asked to find the equation for the time taken, provided that we know that w is greater than u, since that's the condition that's required for the torpedo to actually hit the ship, and given that, we are asked to find the time taken. Now for the first part of the question, what we are first asked to do is to draw the velocity time graphs of these two particles, particle A and particle B, in the same diagram. So let's start off by drawing a velocity time graph that we can then use in order to mark the velocities of the two particles. So here we have the graph. We can see we have the horizontal and vertical axes, and we're also going to have negative axis for the vertical one, since we are going to have negative velocity. So I'm just going to draw that vertical downward axis like this, and we're going to label this velocity, and we're going to label this time. Now given this, if we consider the first particle A is dropped from rest at a height h above the ground at time t equals 0. So at t equals 0, which is this point right here, our particle is dropped vertically downward, which means it has a downward acceleration of g. Now considering this particle, let's assume that vertical upward velocities are positive, and therefore since this particle accelerates in the downward direction like so at an acceleration of g, it must be falling downward, meaning that all of its velocity for the entire time is going to be negative. And considering the negative values that we're going to get, the gradient of the graph is going to be negative g, since the acceleration is the derivative of velocity with respect to time. Now due to this, we're going to have a constant downward acceleration of g, meaning we have negative g on this graph, meaning if we draw the line corresponding to the velocity of the first particle, particle A, it is going to look something like this. We're going to have a line going vertically downward like this at an angle, and this angle is going to be such that the gradient here, I'm going to write gradient, is equal to negative g, and this line is representative of the motion of the particle A. Now considering this line, since the gradient is negative g, if I draw the angle that is there in between the x-axis and this line, which is this angle here, theta, we can see since the gradient here is negative g and this angle theta is going to be negative if we measure it in the clockwise direction, so anti-clockwise direction rather, we can say tangent of negative theta is going to be equal to the gradient of the line, which is negative g, and therefore tan theta is equal to g. So here we can write tan theta is equal to g. Now similarly, if we consider the other particle is projected vertically upwards from a point on the ground with a velocity u. So the particle is pointed upward and has that vertical velocity of u at the start. However, as this particle goes up, it's eventually going to stop and turn around and start falling down due to the fact that it's still under the influence of gravity, and therefore this particle is going to experience a downward acceleration of g. So the initial velocity u is positive since it's in the upward direction, but the acceleration g is negative since it's downward. So on the velocity time graph, we are going to have an intercept. The reason for that is at time t equals 0, which is the initial instant that the two particles are set in motion, the first particle had 0 velocity, but the second particle has a positive velocity u in the upward direction. So therefore we can say it is going to have an intersect at the point u on the velocity axis, and u is a positive value. Now from this point onward, since the particle is constantly going to be accelerating downward, as in the negative direction, it is going to have a negative gradient in its velocity time graph from that point. Now considering this graph, since this particle is going to have a downward acceleration of g, the same as the first particle, it is also going to be represented by a line with the same exact gradient as the first particle's line, but now passing through the point u and 0 on these axes. It's going to intersect at velocity equals u, time equals 0. So due to this, we can see these two lines, this line and this line, are going to be parallel to each other. This line is also going to have a gradient of negative g, and therefore the angle here, this angle, is also going to be such that tangent of the angle is equal to g. So we can see these two lines are parallel to each other. I'm going to mark that separately with the two parallel line marks like this and this. So these two lines are parallel. Now what they're saying is at a certain time t, we are going to have both of these particles being at the same vertical position. They're going to be at the same height from the ground at a time which they are saying is h over u. Now to find this time, I'm going to mark the time on the graph by drawing a vertical line at a certain point, let's say this point right here, and saying at this point the two particles are at the same exact position. So we can see at this time t, which I'm going to call t equals capital T, at this time right here, both of the particles I'm going to suppose are at the same vertical position. Now considering this shape here that we've drawn, we can see if this time is t equals t and this time here is t equals 0, then the distance between these 2 points must be equal to capital T. Due to that, I can mark this length right here as being equal to capital T. Now let's try to solve this by considering the two motions of the two particles and the conditions that are required for both particles to be at the same point. Now the first particle starts vertically above the ground at a certain height h. It starts like this and it's going to go down. The second particle starts at the ground and it's going to go up. So at a certain point, both of these are going to be at the same position, and we can say, if we draw this diagram more nicely, somewhere over maybe here, if we have the ground and this particle, let's say B, goes up a certain distance, and this particle, let's say A, goes down a certain distance like this, we can see if this total height here is h and this height is, let's say, h1 and this height is h2, we can see that h1 plus h2 must be equal to h, meaning that the total distance fallen by A plus the total distance gone up by B must be equal to h. And we can agree that this condition must be true. Now considering the velocity time graph that we have here, we know that the area under velocity time graph, or the area between the graph and the x-axis, which is the time axis, is going to be equal to the displacement from the starting point of each of the particles. Now considering that, we can see if we take a look at the motion of the particle A and this graph, which is representing the motion of the particle B of B, A's graph has this area right here, and the area that we have is negative. You can see the area is under the 0 axis or the x-axis or the time axis, and therefore this area is negative. Now the meaning of negative area is that if we consider the vertical upward direction as positive, the displacement that we have here is negative, or it is in the vertical downward direction. And if we take a look at our diagram here, we can see that must be the case, since A starts from top and goes vertical downward, and therefore h1 is anyway going to be a downward displacement. Now due to this, we can say if this area is the displacement of the particle A from t equals 0 until t equals capital T, and it is in the downward direction, meaning in the upward direction it would be considered negative, then we can go down and say, according to the graph h1, the vertical height fallen by the particle A is going to be equal to the area of this triangle right here. Now in order to properly write this, I'm going to label this triangle based on some points, and I'm also going to label the rest of the diagram based on some points. So let's say we label this point here point P. Since we have O, now we have P. We could then label this point, let's say maybe Q. This point we could label as R, and maybe we label this intersection point right here as S. So now we have a bunch of points, and we can see the triangle that we want to describe here is the triangle OPS. And therefore, we can say H1 is equal to the area of the triangle OPS. Now similarly, if we consider the motion of particle B, we can see the motion of particle B, or the displacement of particle B, from its initial position, which was on the ground, is equal to the area inside of this box. Now considering that area, the area here is the area of the quadrilateral OSQR, and therefore if we go down, we can say H2, which is the vertical displacement of the particle B, which is exactly what this area is representing, is equal to the area OSQR. Therefore going down, we can say H2 is equal to area of the quadrilateral, which actually looks like this. It's not actually proper rectangle, it's a quadrilateral like this. It's the quadrilateral area of OSQR. Now considering these two areas, we can see, we know that h1 plus h2 is equal to capital H, or rather simple H, and therefore we can say simple H is equal to the area of the triangle OPS plus the area of the quadrilateral like this of OSQR. Now considering these two areas, the first area is this area right here, the area of this triangle, and the second area is the area of this quadrilateral here, and we can see the sum of these two areas is the area of the quadrilateral OPQR, and therefore what we have here is the area equal to the area of this shape, which is something like this. It's a shape that looks a bit like that, of OPQR. Now considering OPQR, we can see the sides OR and PQ are vertical, and as we found previously, the sides RQ and OP are parallel to each other. So we can see the vertical sides here are parallel, and these two sides here are parallel, and therefore OPQR is a parallelogram. Now from parallelograms, we know for a parallelogram, all you need to do is to find one of the base heights and the perpendicular height relative to that of that parallelogram in order to find the area of the parallelogram. In this particular case, we can see we actually have both of those values, since this base height here from O to R, or OR length, is equal to U. Since this point O is the origin, meaning it has velocity 0, and this point here is velocity equals U, and therefore this height is U, and we can also see perpendicular to that, this height of the parallelogram is found to be T. according to that we can say the area of this parallelogram here OPQR is equal to U times capital T. So therefore we can see H must be equal to UT, and rearranging we can see T must be equal to H over U. And this right here is the result we wanted to show. We wanted to show that the time t or t equals capital T here, at which both of these particles are at the same vertical position, where this particle A falls a distance h1 and the particle B rises a distance h2, such that capital or rather simple H is equal to h1 plus h2 occurs when we have the time t being equal to h over u. So as a final statement to this question, we can say, therefore, A and B reach the same vertical height at time t equals h over u. And that's going to be the answer for the first part of the question. Now for the second part of the question, part B, we are told that a ship sails with uniform velocity having components u and v in the eastward and northward directions respectively relative to the water. We are then told that when the ship is at a distance d north from a submarine, meaning that the ship is to the north of the submarine or the submarine is to the south of the ship, given this condition, a torpedo is fired from the submarine towards the ship with the intention of hitting the ship with a velocity w. Now, if we go down and consider all of this in a diagram, we can see if we draw the ship somewhere over here, let's say this ship is going to have a velocity component in the horizontal direction eastward like this of u, and a velocity component in the vertical direction northward like this of v. So overall, the resultant velocity of this ship is going to be in this direction. Now considering this ship, if we consider then the relative position of the submarine, since we are told that the ship is going to be in the northward direction at a distance of d from the submarine, we can then conclude that the submarine must be the same distance d to the south of the ship at that point. So therefore, if the ship is here, then if we go southward a distance of d like so, we should find our submarine. So the submarine is somewhere over here. Now considering this, the ship is going to have a path of motion like this along the direction of its velocity, which is going to be a resultant of u and v in this direction. Considering that, if we want a torpedo to be launched from the submarine to hit this ship, we must launch it at an angle like this. Since if we launch it straight up, by the time the submarine's torpedo rather gets to the ship will already be somewhere over here. Due to this, we must aim for somewhere along the path like so. So we can see the submarine is going to aim its torpedo somewhere over here at an angle which I'm going to call theta to the vertical like this. So using this information, let's try to now derive some equations that we can then use in order to find the things that they've asked, which the things that they've asked are, first, to show that W must be greater than U if the torpedo does in fact hit the ship, and secondly, if it does hit the ship, we are asked to find the time taken by the torpedo to hit the ship. Now going down, what we are going to do is to define all of the things that we know, and then we're going to create some equations to find the things that we don't know. So from this, what we know is that the velocity of the ship relative to the earth, which I'm going to call the water for now, since it is in fact the water that we're considering, is equal to u in the horizontal direction like this. So we can say u like this, and v in the vertical direction like this. And we also know that if we have our submarine and we launch a torpedo, it is going to be an angle like this, and therefore we can say the velocity of the submarine's torpedo, which I'm going to call t, with respect to the water, is going to be at a velocity w at some angle which we are going to call theta, and we're going to call this theta to the vertical or northward direction like this. So we have theta here and we have w here, and we can see, given this w and theta, we could break this velocity of the torpedo relative to the water into two components, a vertical component and a horizontal component. Now considering these two components, the vertical component is going to be equal to w cosine theta. The horizontal component is going to be equal to w sine theta. And due to this, we can see both of these velocities, ship relative to water and torpedo relative to water, are broken into perpendicular velocity components. Now considering this, in order to find the time taken by our submarine's torpedo to eventually hit this ship, we need to find the velocity of the submarine torpedo relative to the ship. So therefore what we're looking for is the velocity of the torpedo relative to the ship. Now according to vector addition of these velocity vectors that we have here, we know that the velocity of the torpedo relative to the ship is going to be equal to velocity of the torpedo relative to the water plus the velocity of the water relative to the ship. Now according to this, the velocity of the water relative to the ship is equal to the negative velocity of the ship relative to the water, and therefore what we have here is velocity of torpedo relative to water minus the velocity of the ship relative to the water. Now considering this, what we have is the velocity of torpedo relative to water, which is going to be w cos theta vertically, w not v, w cos theta vertically, and in this direction w sine theta horizontally. And to that we need to add the negative value of the velocity of the ship relative to the water, which is going to be the inverse of this, which is going to be v downward and u leftward, like this. So therefore we need to add the velocity of u this way and v this way. Now according to this, we can see, since both of these are in certain perpendicular directions, we can see that the velocity of the torpedo relative to the ship can be broken into two vertical and horizontal components, and those components can be easily found by considering these vectors. We can see the vertical component is going to be the sum of the vertical components of these two vectors, which is v cosine, or rather w cosine theta, not v cosine theta, w cosine theta, and v downward, which is going to be minus v upward, and therefore in the upward direction we have w cosine theta minus v. Now considering the horizontal direction, we can see we have w sine theta here, but we have u in the leftward direction here, and therefore in the rightward direction we have negative u. Due to this, what we have is w sine theta minus u. So this is the velocity of the torpedo related to the ship. Now, in order to find the time taken and the other things, we need to find the displacement of the torpedo related to the ship. Now considering the geometry here, we can see the ship has a displacement of d in the northward direction relative to the submarine, and therefore the ship has a displacement of d northward from the initial position of launch of the torpedo. Now therefore we can say the displacement of the ship relative to the submarine's torpedo at the very first instant when the torpedo is launched is going to be equal to d, and since we want the final displacement of the submarine's torpedo relative to the ship to be 0 when they collide, we can say that the torpedo relative to the ship must move perfectly vertically upward and cover a total vertical displacement of d. Now due to this, we can see the vertical displacement is d, but the horizontal displacement must be equal to 0. And therefore, if we consider the horizontal velocity here, the horizontal velocity of the torpedo relative to the ship must be equal to 0 for this to work. So we can see, since displacement of the ship relative to the submarine is d in the vertically upward direction, we can say therefore w sine theta minus u times t, where t is the total travel time, must be equal to 0, leading us to w sine theta minus u being equal to 0 since t is not equal to 0, leading us to w sine theta equal u, and finally sine theta equal u over w. So we can get to sine theta equals u over w. Here of course we need to say t not equals 0, and we also need to define what t is. So I'm going to bring all of this stuff down a little bit like so. I'm going to bring it down one line and say we'll actually do t, let's say 0, t sub 0, and we'll say let t sub 0 be the travel time of the torpedo. So according to this, w sine theta minus u times t sub 0, which is the horizontal displacement of the torpedo, must be equal to 0, leading us to sine theta is equal to u over w. Now, since sine theta can only range in between -1 and 1, we can say that since sine theta is less than or equal to 1, we must also have the condition that u over w is less than or equal to 1, leading us to the fact that u must be less than w, or in their case they wrote it as w must be greater than u. So therefore we have the condition that w must be greater than u in order for us to have them colliding and the torpedo actually reaching the submarine. Now given this condition, we can then move on to the second part, which states we need to find the total time taken by the torpedo to move from the submarine onto the ship. So considering this, in the vertical direction, we know that the total displacement we need to cover is d, and we also know that the vertical velocity is w cos theta minus v. And therefore we can say again w cos theta, which is the vertical velocity, minus v, this vertical velocity, times t0 must be equal to the vertical displacement of the torpedo relative to the ship that we need to have in order for the torpedo to collide with the ship, which is going to be equal to d. Now according to this, if we take both sides and we divide, we can see t0 is going to be equal to d divided by w cosine theta minus v. Now considering cosine theta, we can see up here, we know sine theta, and we can write cosine theta in terms of sine theta. We know that sine squared theta plus cosine squared theta is equal to 1 for any angle theta. Therefore, cosine theta is going to be equal to the square root of 1 minus sine squared theta. Now we can say it's positive due to the fact that theta in here in this diagram that we drew was positive. So due to this, I'm going to say, since this angle is positive and is in between 0 and 90 degrees, we are going to assume that cosine theta is going to be equal to the square root of 1 minus sine squared theta. And therefore we can go down and say this time t0 is equal to d divided by w times the square root of 1 minus sine squared theta minus v. Now considering sine squared theta is going to be equal to u squared divided by w squared, and therefore what we have here is d divided by w times the square root of 1 minus u squared over w squared minus v. Now what we can do here is to take this w inside of the square root, and we can take it inside because we know w is positive. So therefore if we do that, we can see we're going to get d over the square root, and on the inside we're going to have w turning into w squared. We're going to have w squared times 1 minus u squared divided by w squared, which is going to be w squared minus u squared. Since the w squared and this w squared would cancel out, we're going to have w squared minus u squared minus v. And therefore, this is going to be the time t0 taken by the torpedo to reach the ship and destroy it. So now that is going to be the end of this question. Now unfortunately, in the marking schemes that I found for this question, there were no marks listed for the question. So for that reason, unfortunately, I will not be able to provide the exact marks and where the marks go for this question. However, you can probably dig a little bit deeper and you might find the answer sheets with the marks awarded for this question somewhere else, maybe in a paper book or maybe somewhere online. I myself couldn't find it easily online. So anyway, that is going to be the end of this question. I hope you enjoyed. If you have any feedback, post them in the comments down below. If you have any such requests, post them in the comments down below as well, or in the comments of my other videos. Thank you for watching, and goodbye.